My name is Robert Macfarlane. I go by Rob. I am currently the Paul M. Cook Associate Professor of Material Science and Engineering here at MIT. I obtained my bachelor's degree at Willamette University in Oregon, a master's degree from Yale, and then a PhD at Northwestern. Prior to coming to MIT, I was a Kavli postdoctoral fellow at Caltech. All of my degrees are in chemistry, and I'm now currently in the material science department. So what led me to MIT was the idea that I wanted to explore research in the chemical sciences that actually had an impact on materials development and the way we think and use materials. So I started out my career at Willamette. My undergraduate degree was actually technically biochemistry, and I received a very good fundamental education in chemical science. From there, I knew I wanted to pursue something more, something bigger, understand chemistry a little bit better, and so that's why I got my graduate degrees in chemical sciences. However, as a graduate student, my work started to blend a little bit more into not just the use of chemical reactions and understanding different chemical phenomena, but how that could be used to build material constructs. So chemistry is often focused on things at the level of individual atoms and molecules and making and breaking bonds, but where it starts to become material science is when you then build that into larger materials, larger structures. You consider the overall interactions beyond just a singular molecular interaction. And so in the course of my PhD, I developed some design principles for self-assembling nanoparticles into complex, higher-ordered structures. But what ultimately was missing from that at the end of my PhD was a way to make it functional and scalable and useful. And so that's why I went to do a postdoc to learn about polymers and polymer synthesis, so that I had a wider variety of tools that I could actually work with. So in the course of that, I started to think not less about chemistry, but I started to think more about both chemistry and the ultimate material application. So understanding things from the level of a chemist's intuition of bonding and chemical interactions, but then translating that up to larger and larger length scales and to higher order sorts of structures and applications. So the Macfarlane Lab is focused on, again, that idea of starting with chemical understanding, chemical intuition, using what we know about making and breaking atomic bonds to be able to make things. The specific role that we sort of fit, where we fit into the MIT ecosystem is understanding how, when you think about the entirety of a material construct, how that chemical intuition allows you to tailor and tinker with different properties to make them more suited for different applications. So we primarily engage in fundamental investigation of chemical science with an eye towards understanding how useful materials, functional applications, different devices might employ the advances that we're developing in our lab. So some of the building blocks we work with, most of them focus on sort of the nanometer length scale. So we work a lot with nanoparticles and nanoparticle self-assembly. We develop a lot of composite architectures where we take nanoparticles and embed them within sort of a polymer medium. And then we think more broadly about how we can employ the concepts of what's called supramolecular chemistry. The idea that when you make a molecule that has a specific geometric shape and distribution of bonds around a given three-dimensional shape or molecular structure, that allows us to tinker with how those molecules essentially interact with one another. And so one of the driving principles of everything we work with is designing molecular, macromolecular, and nanoparticle-based materials that are essentially smart. They know how to interact with other sorts of molecules, nanoparticles, or polymers in a pre-programmed way. We specifically design them and engineer that into the types of constructs we're making so that when we put them all together in a flask or a vial or whatever we're putting them into, they spontaneously organize into some sort of much higher order, much more complex structure.